Okay, everybody, thank you so much for coming to this streaming lecture for COMP2300. This is the first lecture that I'm live streaming from my office, just to make sure that, this is our new way of delivering lectures going forward in this course. I'm really sorry to be here talking with you by distance. I really enjoy being in the lecture theatre with you, getting some direct feedback as we go, but this is a different kind of experience for us all. I think that this is going to be the best way to deliver lectures to you going forward. I'll be able to talk to you pretty much live. We've got about 30 seconds of delay with this system of giving a lecture, but you can be in Microsoft Teams. I've got your comments on the other screen, ready to read out some questions that you guys are asking me and see what's happening in this course. So today we're going to do a few things. I'm going to talk for a while about the first assignment for this course, and then I've got a short topic which is filling in a few loose ends from the last couple of weeks that you might have found. Then next week we're going to have this pause as was announced this week. So next week is week nothing. The week after that is going to be the new week 5. When we do get to week 5, we'll be talking about functions. But for now, we can just pause that. We've got a little bit of time just to slow down, make sure everything is working. So the topic for today is going to be where in memory. I guess I want to just pause on that first and talk about the assignment. So in this course, we have 3 assignments coming up that we've talked about already. The first one is generally released in week 4 and then due in week 6. But because we have this week's pause, we're going to change it around so that it's coming to you as soon as possible. We'll actually be releasing it as soon as we can finish up a few loose ends and get the template organized. So that should be ready for you either today or tomorrow. We're not quite ready with it yet. Then it will be due actually in the mid-semester break, not quite in week 6. Now the reason for that is that week 6 usually comes straight after week 5 and is before the mid-semester break. But because of the pause week, we've got week 5, then 2 weeks of mid-semester break, and then week 6. So it'll be due from you back to us on the last day of the first week of the holiday. There's actually a public holiday on the Friday because of the Easter long weekend. So it's due 23:59 on Thursday of that week. So I'll just show you the draft page for our assignment, and we can have a look and see how things are going to work. Keeping an eye on the comments. If anyone has a question, do chuck it into Microsoft Teams in the comments, and we'll see if I can answer it directly. So I might, whoops, make this a bit bigger. Cool. So I think I've discussed with you that the 3 assignments for this course are all related to sound. So your disco board has a headphone jack on the bottom. You can plug in a regular pair of headphones. And the really exciting thing about that is that you can use that headphone jack to output a continuous sound that you generate in a program. I'm just going to make sure that I'm, whoops. I want to make sure I've got my right. Okay, I'll make myself a bit smaller so you can see this properly. So in the first assignment, you have to use your disco board to create a basic sound, and that's basically the whole assignment. We give you some very specific details about what that sound should be like, which I'm going to tell you about in a minute. Not to spoil the surprise, but the other assignments we've been working on for a few years, and they're really exciting and fun to do. In the second assignment, you start creating some notes with your sound, and in the third assignment, the idea is to connect 2 disco boards together or connect your disco board to itself using physical wires. So I'm just going to go through the details of the first assignment with you. So this is the page which will be updated and released to you as soon as the assignment is out. At this point in time, everything here is still in a little bit of flux. So the assignment is going to be due at the end of the day, 11:59 p.m. on Thursday, 9th of April. That's the Thursday before the Easter long weekend. the way that we deliver you an assignment template and you deliver the assignment through us is through GitLab. So I know that you have all had an experience with GitLab in the first lab and second and third labs, cloning, bringing a template to your computer, editing it, and then pushing it back up to GitLab. Well, first you have to fork that template so that you get your own version of it. The assignment is really the first real test of doing this properly, because you definitely need to make sure that you've forked, cloned, committed to, and pushed the assignment back up, and that all works in order for it to be submitted. If you don't properly commit to it and push it up, then we won't be able to get your assignment, and it will count as not submitted. And actually, if you don't submit the assignment by the deadline and you haven't organized an extension previously, you won't get any marks for this assignment. So we have a hard deadline, and the penalty for late is you don't get any marks. So it's a tough thing for you, but the answer to this is to make sure you understand how GitLab works, to commit early and commit often. Now, I should say that generally this assignment is released at the end of week 4. You get until the end of week 6. That's 2 weeks. In this time frame, at the moment, you will actually get 3 weeks. So you get next week, the pause week, week 5, and then the first week of the break. I don't really want to push it any further back than that due to the pause, because you have other assignments to do after that, and I want to make sure that we start getting through the coursework and building up your skills in a proper way so that you have enough time for all the later assignments as well. So there's 2 parts to this assignment. In the first part, you need to generate a specific sound, which we will tell you the exact details of it. That's called part 1, and that comes out the Disco Board's headphone jack. In part 2, you get to be a little bit more creative, and we ask you to create a sound that you want to create. So you'll have to do a little bit of research about how digital sound works. I've got a bit of information to talk about that with you in the coming weeks, but at the moment, right now, you can sort of just trust that you'll have to be a little bit creative, find some kind of digital waveform that you would like to create, and do that. So your Disco Board has this 3.5mm headphone jack on the bottom, and you can plug in any pair of headphones that has this kind of connector. So a little bit of background about this assignment. The point of this assignment is to create a digital sound sample by sample and send this to the headphone jack. So digital synthesizers have been doing this for many years. It's something which kind of became popular in the 70s. There was electronic instruments before the 1970s, but they were generally analog synthesizers, which had more in common than radios, I suppose, than computers. So once computer technology or small integrated circuit technology became cheap enough, people realized that they could use them to create a continuously changing signal on a wire, just like we were talking about in the digital logic lectures, signals going up and down like a clock, in the range of frequencies that humans can hear. And if you send that signal to a speaker, we will be able to hear it. So you can hear synths or digital synths in popular music. A great example is Kraftwerk, who played synths a lot. Another example, which I'm going to show you in a minute, is the music of video games, which started to get popular in the late 70s and early 80s. So in this assignment, you're actually going to turn your Disco Board into a synthesizer. You will define a program which tells it what kind of voltage to output on that headphone jack. If that voltage is continuously changing at a rate at which humans can hear, then when you plug headphones in, you can hear it. It's really, really fun and exciting to be able to do this kind of task with a Disco Board, because normally when you're writing your computer programs, you might just be doing a little bit of maths or manipulating some text. And in this case, you're controlling something which is quite artistic and interesting. So it's quite a different kind of assignment than you might have done already. So a key part of this assignment is that you have to be controlling this sound in time. So the signal is going up and down at exactly the right frequency. And that's actually one of the challenges for you, is to figure out how to calculate that kind of, do that kind of mathematical calculation. So I'm going to skip forward a little bit here. But I guess the common point is that when you get into your GitLab repository, you'll see that there are actually 2 branches, one for part 1 and part 2. you'll be doing your response to part 1 in that branch and your response to part 2 in the other branch. So both of these branches will have all the setup code you need, and in particular there's a function called init, I-N-I-T, init, which is going to set up your disco board so that it's ready to produce a sound. And there's another function called BSP audio out play sample, and this is the function that you use to actually send a sound to the audio output on your disco board. So the idea is that when you branch using BL, branch with link, we'll talk about that in week 5, but you can just trust me about that right now. When you branch with link to the BSP audio out function, then whatever you have in the lowest 16 bits of R0 will be played on the headphone jack. So the headphone jack's voltage will go to that level that you've indicated. Now this means that calculating what you put in that R0 and then send to the headphone output is up to you. That's actually the challenge of this assignment. I think that some of these concepts may be a little bit new to most of you. It can be a little bit confusing, but in this page we've got this really long FAQ section which actually has heaps of information about how to do this. And in fact, once you read this through, it's not that hard to get a handle of how to do part 1. So now I'll just talk about both these parts and what the challenges are for you. So in part 1, the kind of sound that I want you to create is a triangle wave, and its frequency is going to be 440 Hertz, 440 cycles per second. So if you don't know what a triangle wave is, I can guarantee you've heard one in your life. If you've heard any music at all, it's used all the time in music in video games, and particularly in old video games, which we now think of as like chip tunes. So the reason we have this chip tunes idea is that old video game consoles, like the original Nintendo Entertainment System, had one chip on them which would be controlling the sound, and people have in latter years taken those chips out and used them to create sounds for their music making. So as a great example, I'm just going to play a bit of The Legend of Zelda now. So in part 1 of this assignment, you'll simply have to make the sound as correctly and perfectly as you can. So you have to create the sound, you have to get it to the right frequency. We want you to have a peak-to-peak amplitude of at least half of the total dynamic range. So between OX8000 and OX7FFF, that's the signed 16-bit numbers, which is the total dynamic range of your sound. Does anyone cannot hear the Zelda? Okay, so just picking up back where I left off, for part 1, you just have to make this triangle wave 440 Hertz as perfectly as possible. It's a little bit of extra work to make sure that it's absolutely perfect, so it's up to you to go through this FAQ and make sure that you've checked that it's sounding exactly right. You also have to make sure in part 1 that your code is very readable and that the structure is as good as you can make it. You've learned all about how to do really great control structures in the lectures this week, so I expect you to be using those control structures as we've discussed as well as you possibly can to make sure that it's clear what you're doing in your part 1. Now we get to part 2. So part 2 is a little bit more creative. It puts a little bit more responsibility on you to make sure that you have an assignment submission which is really great. And in fact, I guess, although we don't consider it to be a huge challenge to get right up to almost full marks on part 1, as long as you've got everything perfect, you'll get full marks. With part 2, even getting the first mark is pretty hard. You have to demonstrate that you're doing something that's interesting and you've done it well. So we're asking you to generate a different kind of signal, not the constant frequency triangle wave. You can pick any type of periodic signal you like. We've got a few examples for you here, but of course, you're free to tell us what you think is interesting and do something that's even more interesting than these. So a couple of other interesting options would be perhaps a sawtooth wave or a square wave, like the square waves we had in the Zelda soundtrack sounds. You could do a simple signal with some aspect that changes over time. You could be doing additive synthesis by taking multiple signals and adding them together, doing a weighted sum. You could create something like a simple filter, a digital filter. You could be doing frequency modulation synthesis, so changing one value's frequency in response to another oscillator. Or you could be doing something really wild like wavetable synthesis. Now, I don't expect you to know what these words mean right now, but there's some links here for you to check out to learn about them. And I'll be giving a little bit of an extra lecture sometime soon discussing these different modes of digital synthesis. Now, part 2 is interesting because in part 2, we'll load your code onto a disco board and listen to your sound. And then we won't look at your code. We're going to look at a design document that you've written up to describe what signal you've generated and how you implemented it in ARM assembly language. So I guess this means that it's okay if you don't do the most complicated signal possible. Actually, doing a great design document is what counts. So if you're choosing like, should I do a harder signal or do a better design document? Definitely do the better design document because that's where the marks are for this one. Of course, to get full marks, you do have to do something cool. Now your design document is going to be in PDF format. We only accept 2 pages. I'm going to put in some details here that it needs to be 12-point font and you need to put your name and UID at the top as you put this into your assignment repo. You can't just put it in a text file. That's not right. If you try to submit a text file, the assignment repo won't actually accept it. It's looking for a PDF file for us to look at. Now there's some process for how to do this. Fork the assignment 1 template repository, clone this and work on your fork. Regularly commit and push. I expect you to be able to do these things in Git. Push up your changes, try different things, commit them as you're going, and make sure that your last commits as when you're creating your code, creating your submission, the very last commits on the part 1 and part 2 branches are what we mark. This is in the course policies, but we don't mark any other commits to other branches. Sometimes people try to have different ideas. They want us to look at multiple branches. We don't do that. We'll only mark 1 commit on part 1 branch and 1 commit, the very last one, on part 2 branch for your grade. So there's a little checklist to make sure you have done what we're asked. If you do your assignment early, commit often, and update it as you get better ideas or improve your signal, you're going to be fine. If you wait until 23:58 on Thursday, 9th of April to upload your assignment to GitLab, I guarantee you that you'll have problems because the GitLab server can be a bit slow when everyone is trying to update their assignment at the very last minute. There's not much we can do about that. We do regularly, or our IT section do regularly try to make the GitLab server better able to handle loads from a lot of students, but peak loads with websites are always difficult to handle, even for huge organizations, even for governments. It's a really big problem. So the only thing you can do for that is to be organized, commit early, commit often, and make sure your stuff is in GitLab sooner rather than later. Okay? Now we've got a whole lot of stuff. Actually, there's a lot of details in this FAQ. I'm not going to go through the rest right now. It's something for you to read and make sure that you understand. But for now, I think I've said enough about assignment 1. When we release it soon, you'll get to have start looking at this, and I hope that you get excited about this and start doing it early, because you've learned so many skills about how to be writing ARM programs in assembly over the last few weeks, and this is your chance to really get started doing something fun with it. Okay, closing these. I'm just going to pause for a minute and see if anyone's got any questions. So if you've got a question, chuck it into the Teams discussion, and I'll see if I can answer it. Anyone with a question? Yeah, I can see Aggie is discussing on the Teams about whether you need to have any music skills or synth skills. You don't actually. This assignment is about putting the right number into the right register at the right time. And that's core COMP2300 skills. So we expect you to have that skill of being able to put the right number into the right place at the right time. I don't expect you to have any information about music. This is simply about creating a repetitive signal that puts that number in the right place at the right time for you. I'm just going to give a thumbs up to Aggie for asking a great question. Any other great questions? Yeah, which part of this is the triangle wave? Asked Mitch, who's one of my tutors. It's the bass part. It's a little bit easier to hear if you've got headphones and turn it up, but whoops, I got Adam Neely there. Get rid of that. This part is the triangle. Cool, I think that's all the questions I'm going to get right now. Hopefully the tutors pick some out if they see that you've asked any more in the stream, but I'm going to talk about another topic right now. So I guess this is something which we've talked about a little bit through lectures. I really wanted to get through the important content while we still had in-person lectures, or the important content up to week 4. So we're actually a little bit ahead, and we've done really well getting to this point. But we can take a little bit of a breather this week in preparation for the pause next week, and talk about where things end up in memory when you're running your disco board programs. So just an outline of what's going on in this particular lecture, just a few short topics. I'm going to talk a bit more about the memory map. We're going to talk a little bit about value directives in assembly, and we'll be doing a bit of digging about how exactly that letter equals command works. So that's a really important command for your general knowledge. You need to use it all the time, and it's important that you understand how it works. So where in memory do things go? Now, we've discussed the memory map at length, but I think that it's important to realize that when you're upload or compile and upload some code for your disco board, or you're running the debugger, your code ends up in the code section, right? The usefully named code section. So we've got this much space. In fact, some of you students have realized that when you load from parts of this code section, your disco board gets an error and ends up in the infinite loop area, which is where it ends up when it gets a instruction that it can't deal with, or something it can't interpret. So not all of this code section is full of code. You only have a little bit actually of code right down the bottom. It's only got a little bit of flash memory, and the rest of it is either kind of copies of this looped around, wired up the same way, or it's empty. And if you try to load from it, you end up in the infinite loop. Then you've also got a little bit of SRAM, not a whole 512 megabytes, just a little bit of SRAM there. So when we've been loading and storing instructions in memory, and we've also been loading from code, and you've been storing in code in your week 2 labs. So I guess today's lecture is just a little bit of disambiguation about how these things work, and the different commands that you can do when you're coding in assembly on ARM in order to get information into those different parts of your disco board's memory map. Whoop. So this is something you will have now had quite a bit of experience with, the value directives in assembler code. So I think you'll remember when you were starting to, just in your very early labs, you were starting to insert words, these ones, and half words, these ones, into your memory to try to make a handcrafted instruction. And we also talked a little bit about ASCIIs. So just as a recap, when you type .word, you could type, for instance, .word OX 1, 2, 3, 4, 5, 6, 7, 8. If you put this in your disco board program, then this 32-bit value will just end up in your code section as if it was an instruction. But if it's not a real instruction, when your program counter gets to it, your program will crash because it's not meant to understand what 1, 2, 3, 4, 5, 6, 7, 8 means. You have to have something in here which is a real instruction in order for the disco board to understand it as code. If you put in .h word, you can do a word that's 16 bits, or half a word, 1, 2, 3, 4. There's another one which you maybe haven't used, which is byte, and this lets you just insert 1 byte or 2 hex values into your instruction stream. And then in our earlier lectures this week and in the Shouty McShoutface demo, I recorded that and have it on Microsoft Stream already. You might have seen this ASCIIs directive. So if you type .ASCIIs, then you can insert a stream of letters, which are then interpreted as bytes. So remember C was something like OX63, and all the other ones I can't remember, but each of those letters translates to 1 byte, and ASCIIs will mean that it's inserted. If you just put that in your code right next to your, as part of your main function, it will just be inserted into your instruction stream. I guess the difference between ASCII and ASCIIs is that with ASCIIs, we always have a 0 at the end. And that was important when we were doing our Shouty McShoutface demo. We wanted to move through a string and then stop when we got to a 0. So we really needed to make sure there was a 0 on the end. With the ASCII directive, it's not going to have that 0. So you can just import the bytes of the letters into your instruction stream or into memory using a method I'll show you in a minute without the 0. I just realized that my head is right over these directives in the slide. I should make sure the slides are all right justified if I'm going to do it this way. Or actually, I think I have another. I have my head in a different place in another view. All right, just small. Okay, my head's out of the way now. So, whoops. There's ASCII and ASCIIs, which I was talking about. I guess I'll have to have a look at these slides and make sure that they're compatible with having my head over them while I'm giving these lectures. So then we have other ways of getting information into your disco board. If you have a couple of different values you want to put in together, you can use multiple values. So rather than just having 1 byte, you could have a bunch of bytes separated by commas, putting into your instruction stream. So here we have OXF2, we know that's a byte, but because we've said that this is going to be a byte, this one is going to get represented as OX05, this will be represented as OX01, and this one will have 0 padding to make sure it's a byte, even though it's only got 6 bits. 1, 0, 1, 1, 0, 0. Similarly with H word, we're going to have 6 bytes here. That's going to be OX00, OX000, OX000, OX1234. And then with word, we'll get 8 bytes in total, 4 bytes for that one and 4 bytes for this one, even though we've only specified 4 bits of information right there. So let's just do a little example. We know that when you do adds R2, R0, R1, we end up with this instruction. There's the R2, there's the R0, and there's the R1. I think that's how it works. And then if you do hword ox ffa3, what are you going to get? Well, just as with the inserting things into the blank in adds, inserting R1 there, R0 here, and R2 over here, we're going to get that F stuck in here, those four, this F stuck in here, these four, this A stuck in these four, and this 3 stuck in these four. Okay, so that'll be something like 1, 1, 1, 1, another F 1, 1, 1, 1, an A 1, 0, 1, 0, whoops, and a 3, 0, 0, 1, 1. So just to make sure we're clear on this, when you do this hword ffa3, if you just type this in your program as you're editing it, like this, .word, whoops, hword ox ffa3, actually we can just compile it and have a look at what happens. Because this isn't a real instruction, unless we're really sure that it's an instruction that should make sense, we're not going to get anything to happen when we run it. So when I try to run it, I just end up in this is called the default handler. This means that the disco board has had an error, so it's going to end up in this area of code because it doesn't know what to do. It has to do something, it ends up in the default handler, which just has an infinite loop. So we go nowhere. I'll just run this program again and we can have a look at the memory to find out what happens. I'm just going to disassemble. Blah. I don't know why can't say disassembly then. I want the main function. Actually, there was my ended up backwards. Oops. Indianness. Sorry, guys. It knows that this is not a real function, so it doesn't know what to do with it. Okay. Wonder what happens if we look in the memory map and see where those are. So it should be 0800 0188. 0800 0188. I just want 32 bytes. Interpreted as decimal. View memory, OX 0800. What was it? 11. I can never remember. 0188. Someone's asked in the chat if later assignments involve making music. No. Memory. OX 0800 0188. They do. All of the later assignments involve making music. So get used to it at this point of the course so that you're prepared for later. So we've got our OOBF, and then we've got our word in little endian format. So, oops, just going back to my slides, I can just illustrate how wrong I was. So of course, it's going to start with this byte in memory, and then it will do this byte because it's little endian. That one, and then that one. Of course, if we're writing it down as big endian format, we'll still write it down in this way, but it's certainly going to be flipped around when it's in memory so that we start with the low part. Okay, oops. Ben Gray has just answered in the chat, all of the later assignments do involve using the audio output. So I suppose they're musical in that respect. You don't have to compose music yourself. You can just follow the instructions and do as we have suggested, and you can certainly get great marks on all of these assignments. But if you do want to create some music, then you're completely welcome to do that too. There's option to be as creative as you want to be. Now I'm going to talk about another memory command, which we haven't seen that much. It certainly comes up regularly as we're going on in this course, and that's to add an offset to your instructions you're going. So recall that the litter and store, or load register and store register operations require a memory address, and we put that inside these little brackets. R1 has little brackets around it, and that's our memory address, interpreting R1 as a memory address. So there's also, as you've seen on your cheat sheet, offset versions of these instructions, which means that you give your address in R1, and then you have a load value. You're loading the value which is not at R1, in fact, but is moving 4 bytes past R1. And in this case, we're going to do a store. In this case, we're loading from that address, R1 plus 4 bytes. In this case, we're storing to R1 minus 4 bytes. And there's actually also a register version of this as well, which looks like this. Store R0, comma, R1, R2. So this instruction is going to store the value of R0 in the memory address R1, stored in R1, offset by R2. Now, if you remember in the Shouty McShoutface demo, I did a little bit of maths to generate an offset memory address. Suppose I had R1 as my memory. I'll just start a Blackboard to do this. Maybe I was storing some memory in R1, or storing an address there, mov R1, comma, OX20000000. That's our mem address. And then I also wanted to have my offset, which is going to be mov R2, OX7, maybe 7 bytes. And then when I was doing my load in Shouty McShoutface, I would do something like letter R3. Well, I would first of all add these together. Add, maybe I'll use R3 for the adding, and I'll use this one, R0, for the address I'm going to load to. Add R3, R2, R1, and then I would do R3 here. But actually, I don't need to do this. Oops, I went a bit wild there. I don't need to do this. I can just go letter R0, R1 as my base address, comma, R2. And then I can keep changing R2 to move through my sequence of characters in memory. It's a really handy trick to use. The memory address here is still in square brackets, but it's now got this offset, or a little bit of a calculation that happens before your memory address is used. So I guess we can just pause for a minute and think about when we might use this. I gave you one scenario, which was, I suppose, looking at a memory address in, or the address of a string in memory. But why don't you have a think and type in Microsoft Teams? We'll see if anyone bites. Type in to see how this could be used. I'll start typing in to see who wants to join in. I'm gonna have a sip of water while I'm waiting. I know I've got 49 live viewers, so some of you have got to get onto the chat and start talking to me. Yeah, Yansong is saying, well, maybe you could do this in the assignment to place the right value. Maybe. I don't think that the assignment is exactly where you need to do these loads and stores. In fact, I'm not really sure that you need memory loading and storing for the assignment, unless perhaps you were doing one, or at least part one. If you were doing something advanced, you might need to use memory. Whoops. Yeah, so, but the assignment is a good idea, but maybe think of some other things that we've been doing in your labs already. For instance, if you had some data from your Hearth Pebble game that you've been designing in Lab 3, how could you use offset load and store for that? Yeah, that's a great idea, actually. Isabel came up with one, and she says that it's bad. I think it's quite good. So maybe you have a memory address, or you've got all of your players' names or something in memory lined up. So you might have like strings. One might be, oops, where's my marker? One might be Charles, and one might be, and we may know that this is 1, 2, 3, 4, 5, 6, 7, 8. So we've got 2 extra bytes there. Everything's 8 bytes long, and then we've got Isabel, 1, 2, 3, 4, 5, 6, 7, 8. And we might know that mine is offset 0 and Isabel is offset 8. So if we wanted to load up the player whose turn it was, we could be storing something as an offset and make sure that we load the correct name or something. I don't know, you might have some structure like that to store your names. Yeah, and Joseph has had another good idea. If you've got some data with an unknown length, it could be an array. An array is sort of just a sequence of memory addresses, of chunks of memory that you're using for something that are the same length. So this could be an array of all the players. Just combine these two examples. Could have Charles, we know that this is going to be 8 bytes long, 8 bytes. We know that Isabel is going to be 8 bytes long. And then we could have Joseph, 1, 2, 3, 4, 5, 6, 7, 8. That's going to be 8 bytes long. See what Jia-Jun Liu was saying. When we try to use recursion, yeah, totally. We'd certainly need this when we're using recursion. I think recursion is a bit more of a complicated topic, but just to maybe, wow, where's my... We've got multiple conversations here. I think I'm going to move everything to, let's move everything to the first conversation. Everything to this reply chain now. Yeah, just to finish off talking about Joseph's thing, you'd want to start, if we know that each of these is 8 bytes in length, then we might store our offset of whose name it's going to be by 0, 1, and 2. And then when we calculate the offset, we might do like mul 0, whoops, mul doesn't have a immediate value function, whoops. Yeah, essentially we're going to do 0 times 8. We're going in assembly language later. If we can do it in maths, it's not too hard to convert into assembly language. So we're going to do 0 times 8. If you want to get my name, we'll do 1 times 8 as our offset if we want Isabel's name, and then we do 2 times 8 if we wanted Joseph's name. So that would be useful as well. Yeah, Joseph's saying, of course, we're probably going to use the stack for recursion, which is exactly true. We are going to use the stack. But sometimes you might have stored a data structure on the stack, Joseph, and then you would want to, or an array, and then you might want to use a offset value to get to it. And in fact, when you're using the stack, you mostly store your addresses on the stack in terms of the start of your local kind of stack, or your frame in the stack, and then you'll want to use offset addressing to get to that as well. So have a think about that. Yeah, totally. Yeah. So you need to use offset addresses to navigate around the stack as well. Yeah, so I mean the offset address function, this is not like a little bit of extra stuff. This is super useful all the time when you're doing assembly programming, because you often know a base address and then you know how far away you are from it, and then you can get that address in one step with the offset address. And in fact, it makes more sense to use this command than to do the arithmetic and calculate your new address, because it's clear in the command that you're trying to get to an offset and that you're not using your arithmetic to get some other value or overwrite your base value. So it's not only useful, but it also clarifies your program a little bit to use it. Okay, I might call that a halt to this talk session here. Thanks you three for jumping in with a few examples, or you four actually. That was really fun to try that. Buckets, I don't know, can't do buckets when we're, well, I suppose we can do buckets on the stream as well. We can do buckets at the best of times. So you know this one might be our base address. That's the base. And then we might say that we want to go across 4 bytes. Remember that all of our memory is byte addressed. So we go +1, +2, +3. I suppose we would have to go across 3 to get to there. And then we'd actually be reading our value from there. That would be letter R0, maybe R0 there, R1, comma 3. So that's when we do letter R0, comma 3, or R1, comma 3 in the address part, we're going to get out of this bucket. Now, if we change our offset to maybe 6, 7, 8, 3, 4, 5, 6, we'll end up coming out of this bucket instead. And if we change our base to somewhere else, maybe down here, then we're going to get out of this bucket instead. So we can kind of navigate around memory, moving our base to different places, and then also moving our offset to find where we are within that memory structure if we have some regular structure. We do come right back to memory structures in week 7. We talk about data structures in detail, and we talk about data structures, or the stack structure in particular, in week 5 when we talk about recursion. When we talk about functions, which do involve recursion. So we'll get to this in a bit more detail later. Now, let's go back to this idea of value encodings with our instructions. So if you're using the .word value encoding just to put a value into your instruction stream, there's been some questions about this on Piazza. Someone will say, oh, well, I did this .word deadbeef thing, and I moved my debug pointer over and I ended up in the infinite loop. What's gone wrong? Well, nothing's gone wrong. That's the way it's supposed to work. But sometimes there are ways to use the instruction or the data insert functions, .word, or insert directives, .word, .hword, .byte, .ascii, .asciies, and not go into the infinite loop. And what you need to do is make sure that your program counter never gets to that bit of data. So you've actually stored a bit of data in your instruction stream that's now like read-only. It's never going to be used. It's stuck there forever. It's never going to be written over, never going to be changed. You can read from it, but you can't put the program counter there. And that's perfectly fine. So this is a good example. This may look a little bit odd to start with, but let's just run it and see what happens. So I'm going to go back to my main.s function. I think my head's going to be in the right place. It should be down here somewhere. And I've got my, I'm going to put this .align2 thing in here. That's just a little bit of like appeasing the gods of assembly to make sure that our data is correctly aligned to 2-byte boundaries. And I'm going to put in a word, and it's going to be dead beef. Actually, I don't want to use dead beef. It's a bit too meat-eatery. Maybe 8 bad food. I hope none of you have eaten bad food. 8 bad food. There's actually not that much bad food in the supermarkets because everyone's buying all the non-perishable things. Plenty of good food around though. Lots of great vegetables. So there's lots of, if you like eating fresh food, it's no problem of doing that at the moment. We've got 8 bad food here, and I'm going to try loading into R0. I'm going to put in program counter, and then the offset of 4. So I guess the question on the slide was, like, what's going to happen in this program? We're loading something from the program counter offsetting 4. And we've got our branch main. So let's just run it, and I'm not going to actually run that, that line of code. I'm just going to have a look in memory what ends up in there. I need to stop and start again, building a new program. So our program counter right now is at 0x8000 should be there, 180. Yeah. So we've got our 8 bad food, 8b add foo odd. Here's our first instruction, that's the litter instruction, I think. And then we've got a branch in there, and then we've got the 8 bad food. So if we just kept going forward, then our down and down, if we didn't have this branch here, we'd end up at the 8 bad food bit, and we'd be trying to interpret an instruction or run an instruction which isn't one. 8 bad food is not an instruction. But because we've got the branch here, we're just going to keep stuck in this little loop, and we're never going to overwrite that or try to execute this value. So this is fine. Even though this word is in the instruction stream, we can still operate this way. So you might have guessed what's going to happen if I run this line of code. It actually loads up 8 bad food. So the program counter, when we were here, the program counter was going to be at the branch, which is a 4-byte instruction. It's going to load up this 8 bad food, which is the very next thing in our instruction stream. There's the 1, 2, 3, 4, 5, 6, 7, 8 bytes. The counter will be here. I think branch is an 8-byte instruction. Ben Gray will correct me in the comments if I'm wrong. We were here, that's the loader instruction. Here is potentially the branch instruction. So that's where the program counter is going to be after, when we're resting here, about to run this line of code. It's going to try to load up whatever is 4 plus, so that's 1 plus, 2 plus, 3 plus, or 1 plus, 2 plus, 3 plus, 4 plus. So here we've got 8 bad food in little endian format, and that's what's going to get loaded into R0. So that's handy, isn't it? I might just try disassembling it so we can see what it looks like. Disassemble. Oh, come on. I'm not in a debug configuration, that's why I can't disassemble. Okay, there's our 0148. And oh yeah, we've got FF, F7, FD, BF. That's so 16 bits for the litter, and 32 bits for the branch. And then we've got 32 bits of nothing, or 16 bits of nothing just chucked in there to make sure we're not doing anything. And then the 8 bad food. So that was what the dotted line was going to do, just push things forward so they're aligned to a boundary. So this brings us back to the litter equals, the pseudo instruction for litter. That's actually what it's called. When you put this equals sign into a litter instruction, it's not a real load register. It's called the load register pseudo instruction. And the reason for that is that the assembler might actually produce a different instruction than what you put in. So I've discussed this with you before and sort of presented it as an alternate way of getting any 32-bit value you want into a register, no matter what. And that's exactly what it does. It is going to, if it can, it's going to use mov. And if it can't use mov, because maybe we've discussed this, that mov has only a limited number of instructions that are possible for it to represent, or it's only got a limited number of values that it can represent, then instead it uses a litter and it cleverly stores this word somewhere else in the instruction stream and loads it for you. So it's actually the assembler doing this work on your behalf. It's not your disco board doing it. So if you use this, the assembler sees it and then deletes it, puts in the best way of doing it for you, and then sends that to the disco board instead. So it's a pseudo instruction. You can have a look at this link if you're interested in exactly how it works later. This ARM website's just so slow. Very frustrating. Okay, here's the letter pseudo instruction, and you can see all of the details in there. So let's give it a go. We might try it with this same word. Letter R0 equals OX8 bad food. Cool. And we can get rid of this stuff. See what happens. Okay, now I don't want to spoil the surprise, but you can kind of see that it's done exactly the same thing. We've got 0148, that's our load. We've got our branch instruction there. Then we've got a couple of bytes of nothing. And then we've got 8 bad food. So really the letter pseudo instruction has done an offset by the program counter. We can prove that by just doing the disassembly of main and see now that, whoops, move this over so we can see properly, that it's done 0148 letter PC plus 4 bytes forward to get us to OX800190, which is this byte. It's going to load those 4 bytes for us. So this is really nice that we have this feature. It means we don't really have to worry too much about whether our values can be encoded by mov or not. Of course, if it's a small value, less than 8 bits, less than 256, you can always put it into your mov function. But if it's bigger, you might not be able to. So I might just try a small value and see how it goes. What about 7? Let's see what happens now. Okay, so now I don't think we're going to have our 0007 or anything in there, so it hasn't stored it in memory. We'll just have a look at the disassembly for main. Oh yeah? What? I thought it was going to do something different. Does it work? $190. Oh, that's odd. Oh, maybe that's the previous one. Nope. Oh well, I'll figure this out later. But no matter what value you put in there, what 32-bit value, Litter will always give you something that you want. Oh, the disassembly view is old. That's what Benjamin's telling me. Well, Benjamin, come and tell me how to do it then. If you've only got criticism from the chat. I'm going to start again. Compile it and run my disassembly view. It's doing the same thing. Oh, okay. Some kind of bug means it doesn't update properly. Okay. What if I close everything and start again? Will that help it? It's great when I'm doing these lectures streaming because I can just waste time and you guys don't have a choice but to keep watching me. So, is that good or bad? I'm not sure. There's no one trying to get into the lecture theatre after me. Okay, do my debug. Okay, we finally got there. So it's not using the litter function, it's using mov with number 7 because it knows it can, right? The assembler has all the details of how your disco board works. It has all the details of the instruction set architecture, and it can, in some cases, give you the best instruction for the job, and you don't have to worry as much about it, which is great as a programmer. So feel free to use this litter instruction if you think that it's going to be an issue with mov. If we're just doing 1 and 2, mov R0, mov R0, 24, right? That's definitely less than 8 bits. I guess I was just going to point at this point to where you find out about this immediate value encoding. Now we do have, I'll just note to Ben that I fixed it. Fixed it finally. Yeah, Aggie, I guess there are sections that could be blurry in the videos. It's certainly not the internet at my end. We've got a really good connection here. Maybe Microsoft Stream is a little bit dodgy. But definitely give us a review in the comments on Piazza. Tell me how your experience was. We might end up using another solution, but I still think that this is much more exciting than me just talking to you in a lecture theatre with no face or ability to do this kind of screen sharing stuff. So hopefully this is a workable solution. The ARM immediate encoding is a little bit tricky, and I guess this website, Alistair Diarmid's website, gives you all the details. And the trick here is that, we find our instruction. I suppose it doesn't give you exactly the mov instruction, does it? If I go down to here, the mov instruction in the ARM v7 ISA gives you 12 bits of immediate values. So there's 8 main bits of the immediate, and then there's 4 extra bits to rotate it. So the 8 main bits can represent any number that fits in 8 bits. So any signed number between 0 and 255, or any unsigned number between 0 and 255, or any signed number between 127 and minus 128. So actually the rotate thing, you've got 16 different options, and it can take your 8-bit number represented here and shift it or rotate it around the whole range at 2-bit offset. So it can't rotate it it can't represent all of the 32-bit chunks, but it can move it around as much as you want it to. So that's really, really handy. And it lets you specify some values which are, I guess, more useful because they're more able to represent things in memory that you might want to pick up. If you're just loading a value from memory, you might find it useful just to use the one mov, or the pseudo instruction will use that mov for you if it can. And it does let you access more interesting values than you previously could. I think this is not all the right values. Maybe someone in the comments is going to tell me in a minute that it can represent more. I seem to remember that it could copy them into various places as well, but maybe this is the way it is. Someone will tell me in a minute. Anyway, the details are in the ARM v7 architecture manual, and I encourage you to try to get in there and get that information, even though it's really tough going. So I guess, it's a perennial comment when we get to this stage of the course. People understand everything about this course, but they really don't understand what's going on with dead beef. Why are we using dead beef all the time? Well, it's called a numeric literal value, and these are often used when programming something where you're operating with the machine instructions and viewing memory often, just to make sure you know where you are. So OX dead beef is used a lot. 8 bad food is used in iOS. There's a list of them on Wikipedia. If you're interested, you can have a look at the rest. Magic numbers, there's some others. Bad, 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 bad. Beef case. Bad beef, CCCCCC. And there's nothing special about these from the perspective of your disco board or from any CPU. All that they mean is that there's something that when you're scrolling down through the memory view of your disassembler, you can see, oh, that's where that value is. Now I know where I am. I can work out where I am in relation to that, because all the other values don't make much sense when looking in the disassembly view. Now we've already done this a little bit, but you can actually do this pattern all the time for using the lit pseudo instruction. In fact, it's probably the one that I use most in the work in this course, is we've got some label, loop. Of course, loop means the memory address of this instruction in memory, in the instruction stream. And then liter R0 equals loop is going to load the address of that label, which is going to be its own address. So this is very meta now. Liter R0 equals loop is grabbing the address of this very same instruction and putting it into R0. So this is something we use all the time in order to pick up the address of a function or the address of a bit of data which we know is in memory, and you'll be using it throughout this course. We've already used it in the Shouty McShoutface demo. I guess now we're starting to use data more and use code more. And we need to be a little bit careful about code and data, because from the perspective of your disco board, there isn't any difference between code and data. They're all just ones and zeros stored in memory. When we look in the memory view, I've lost my memory view, but if we did look in the memory view, we'd see that the dead beef numbers are just hex digits. They just happen to be ones that are meaningful to us. But the disco board's just going to try to run them if you push forward in your program and move past them. So we know that you can put instructions in your program using HWord. You did that in week 2. And you can also put data into your program using assembly instructions, which we've tried in the Shouty McShoutface demo. I'm just going to clarify that a little bit in the next few slides to make sure this is all clear. All these data instructions and all of the code that we put in is just zeros and ones. The code happens to be special numbers that the disco board can recognize. So you have to keep this in mind when you're writing your programs. Is the assembly code that you're writing, which parts of it are going to get encoded to data in memory? What kind of zeros and ones is it going to get encoded into? Are they instructions that your program counter should be pointing to that you're then going to try to execute? Or should they be bits of data that you're trying to use loader and store on to use as variables during your program? Now, I've used this in the Shouty McShoutface demo, actually in the demos in week 3 as well. This thing called .data, you might have seen me do that before. So it's called an assembler directive. .data is not really an assembly instruction. Now we've got shift options for our board. Thanks to, yeah, I thought so. The shift instructions, you actually get 5 bits of shift, not 4. And one of them lets you sort of copy your 8 bits across. Finally we got that information. I knew it was different. Yeah, okay, back to .data. The .data assembler directive, it's not an assembly instruction. It's something which your assembler and the linker is going to operate on to make sure that our data goes into the right place when we execute a program on our disco board. So you can see this is the typical kind of pattern. We already did this in week 3. I've got a .data section, and everything here ends up getting put into SRAM on our disco board. When it runs, it'll get copied into SRAM. And I've put a label here so that we know where that information is. So if I put .word, I've got liter R0 equals stuff. That's this label. That means it's going to get the address of stuff, the address of this word. And liter is going to load that word of data into memory. We've already tried this in week 3, so I hope it's something that you remember. But the important bit now is this data directive. So I guess I already gave the game away, or by discussing this in previous times, but the question is, what is R0 going to be after the second line of this program has been executed? So the first line is going to be, first line loads that address into R0. And what does this line do? Well, the load function loads things that are at this address and they go into R1. So actually R0 is not going to get changed. It'll still have the address of stuff. And I know that if this is all the data we have in our program, all the .data section we have, it's going to start at the first address of data, which I just happen to know is 0x2000000. So that's what the stuff label is going to be. So R0 is going to have this number in it. That'll go into R0. And then R1 will have OX dead beef in it. Dead beef, not vegan friendly. You can certainly use these little magic numbers in your programs. They're fun if you want to be debugging something and check what you've got in your memory, but maybe you'll think of something else that's interesting, not dead beef. So what did we just do in the previous program? We put some data in SRAM near this value. Probably if it's the only data you're going to put in there, it's going to be at OX2000000 using the data section. Then we read, modified, and we can write back a new value. I suppose I should do it in a demo for you. Letter, I'm going to use a different word .data here. Maybe I'll put the directive, the label Charles word there. And then I won't use dead beef. I might use OX ABCD, ABCD. Load Charles word. Letter, I'm going to use R1 for that, or R0, yeah. Letter R1, address of R0. Now I might add R1, 1, and then store it back. Just a little memory demo. So there's the word I'm going to store in memory. I'll just get this building. That's the word I'm going to, whoa. What did I do? Charles Word, not Charles World. Whoops. Okay, so I've loaded Charles Word into memory, which is OX2000. Let's check the memory viewer, make sure I know what's in there. View memory, OX2000. Get 32 bytes of memory. There's my word, ABCD, ABCD in little endian format. Load that into R1, there it is. I'll add 1 to it, ABCD, ABCE, and then store it back, and then back we go into memory. So this is a basic little programming pattern for you to use a bit of memory for a variable. In this case, we're initializing it with this value, but you could of course just initialize it with nothing, OX00. And then we can use this label kind of like a variable throughout your program if you want to store a special value there and get it back later. Now we actually have to use the data section for this kind of work. We can't use the code section. If we did this without the data section, Charles Word's going to end up in code and then we won't be able to store to it. So the Disco board doesn't let you store to things in your regular flash. It only lets you store to things in SRAM. Oops. So you need to use that SRAM to store your variables as you're running your program. So there's stuff in the loop copy data in it here. This is in your startup. I think it's in here somewhere. Copy data in it. This gets your SRAM all set up and puts things into the right places. You don't need to worry too much about what goes on there, but if you happen to delete that stuff, your programs probably won't work if you're trying, especially if you're trying to use memory. Oops, I don't want to open Emacs. That's the danger of live streaming. I might end up opening the wrong things. So I guess one other question you could have is there a directive, an assembler directive for writing code as well as for putting things into memory? Well, actually there is, and it's called .text instead of .code, and it's actually the default section. So you can use this if you want to. You can actually end up with writing a bunch of code in here, .text some code, then do some data, and then maybe write a little bit more text and turn this back to code. And we discussed a little bit earlier in last week when we were thinking about where things go in memory, actually the linker file that runs on your program after it's been assembled, it gets assembled, then linked, then uploaded, that will put these things in the right place and make sure they all get put into memory. And I think I discussed with you when we were doing a previous demo that if you do use this data directive and you take out the bit where you actually load it, your linker doesn't bother to put it in memory. It's only going to put into memory things that you're using. So you need to both have the label here, the word here, and use it in your program. Otherwise, it's not going to go onto your disco board. We just should remember that .text and .data are not labels. They're assembly directives. So they're information for the assembler to do work for you, not information for your disco board to do work for you. So they don't ever exist on the disco board. Everything is sorted out for you before the data gets there. A little bit of extra reading and then a few more slides. I think I might put in some readings from our online book. You might like to check these slides after this lecture. I'll put in a few extra links to understand this stuff. I guess we're going to go to a question section now, but oh yeah. We can call that the end of the lecture. I think it's 4:26. I'm going to stay online for a little bit. If you've got any questions, then feel free to ask them in the chat and I'll answer in the stream as well. And I just want to thank everyone who's been watching. There's 37 people in the lecture theatre right now watching this live stream. I think there were about 50 when we started, so there's definitely a few people who are interested in seeing it live. Let me know how your experience is and do ask any questions you've got. Just type in any last questions for... Thanks, Leopold. I just got a message from Leopold saying the stream worked well, so I'm really trying my best to provide an experience for everybody that's fun. It's also kind of fun to stream things online, so I guess it's done a little bit of learning for you guys to see what's happening. I'll take a selfie with my setup so you can see what it looks like. I love my keyboard sound, yeah. I've got a nice clicky keyboard in my office, so we can... I got my light set up here. Whoops. And a green screen behind me, which you can't see because it's getting filtered out. But there's my green screen in my office. And got a bunch of lights to make this look cool. So I'm trying to make an experience which is a little bit nicer than just standing in front of slides in Coombs Lecture Theatre. Of course, it's nice in the moment when I'm there, but if I don't happen to be in the lecture theatre, it's hard to get it to work well. Aggie seemed to like it. Keep your feet up. Yep, certainly easier. Yeah, okay, I might call that the end of the stream. I'm going to put on the outro for everybody, so have a great weekend. Next week's the pause week, so we're literally doing nothing next week. I'm going to be working on generating all the course content for you. If you look on the lectures page, actually I'll show you that right now. I've now got the lectures page in a little bit of a better state. So I've got this is really big right now, but I've got this big list of every lecture we're going to do in the course. There's only 2 of them which are unfinished. The interrupts one and the asynchronism one are a little bit unfinished. I haven't prepared that lecture yet, so I'm just working on that at the moment. Every other lecture in the course is prepared, and we have videos from all of the lectures we've done so far. And all of the lectures we haven't done so far, I've got the videos from last year. So you'll either see me or see another teacher teaching these concepts. So if you want to get ahead with your study and take advantage of next week, then that's fine. You've got the information here to do it. All the labs from last year are ready to go as well. We're going to get the assignment to you as soon as possible. But also, this is a really difficult time. Part of the reason of having a pause next week was to make sure you can do the things that are necessary, set your life up so that you're ready to be practicing good social distancing, looking after loved ones, getting home if you need to, and ready to sit tight for the next 6 months. So if you have to get somewhere, do it now. If you can sit tight here with us in Canberra, then do that too, and make sure that you're ready for what could be pretty tough over the next few weeks. But I'm going to try to provide you with as much information as possible about this course as soon as possible so that you can get your study done first, and then if something in your life has to change, maybe you can take a week out a bit later and you'll still be okay. So make sure you're up to date with everything and get it all organized. Zhexiang has a last minute question about the hurdle test. We're going to publish the results about the hurdle test as soon as we've done everyone's tests. So that's actually may not be until week 5. We've done every test. It's going to be in week 5. So next week is a pause, and then week 5 is when we normally release the results of the hurdle test. So I can't do them next week. We won't be ready. We're actually going to pause on that stuff as well and get back to it in week 5, make sure we've caught up with everyone. So I hope that's okay. Thank you so much for everyone for doing your hurdle tests this week. We got through the vast majority of them. But because of this current crisis, it's been a little bit hard to catch up with some people. Some people were sick, couldn't come to campus. Some people couldn't make the remote call we were doing. So we'll be ready in week 5 with them, but not next week. It's not week 5, it's week nothing. Okay, any other last minute questions? Otherwise, I might call it. Thanks, team. See you next time.